The problems, of course, that was always in the details. The economics kind of suck. The power companies are getting screwed because nobody's giving them money. And they still got to operate the grid. So nowadays, on-grid kind of has some sticky wickets because now they charge you just for having the grid connected to your house. Then they don't pay you the same rate that you pay them for the electricity when you need it. Understand what I'm saying? So it's not like a panacea, but this is way better than that. Every solar panel you've ever seen on any house ever is this. Unless you've been on the run from the FBI too. Raise your hand if you'd like to ask me a question about this. Then there's another type of solar power, please look up, where you're creating heat to make steam to spin a turbine. You've got small scale, old school parabolic mirrors. Parabola, you know the parabola? Parabolic mirrors. The parabolic, they're shaped like a parabola. Yes? No, I mean, coincidentally, they kind of get hot because they're out in the sun. Like rods. You're not using the heat for any beneficial purpose. No, there's no transformation of heat into anything there. It's just you're out in the sun. Here, though, you are using the heat. That's what it's called thermal. Thermal, solar electricity. Light into volts is like electricity making. This is heat making. Because the heat can be transferred someplace else. And if I have Homeboy's water bottle and I stick a hot pipe in there, that's going to make that water boil. So I can carry the heat to someplace to make steam. Does that make sense to everyone? I move the heat as a heat exchanger. Yeah? So I make heat in those pipes. That's not water in those pipes, by the way. It's usually like an oil or a super salt. Like extra saturated salt water, like 60% salt water. Super salty. So it can't boil, it just gets really, really hot. Like oil that's super, super hot, but it won't evaporate. So I get those pipes like really, really hot, and then please look at me. I can just move that medium to carry heat away somewhere else to make steam to spin a turbine. Please look up right there. That's what that red coil is. That's the hot pipe coming from the parabolic mirrors. But it turns out that's not that good. I don't know. People have tried it out. Doesn't really make sense. The cost of operation, the amount of heat you get, the amount of steam you can make, the amount of electricity you can make. It's like, man, that was 1.0 and we pretty much moved on. Like that really doesn't. I'm not aware of anybody trying to make money on that. That's not really working. It's a free market. You got to make money, right? This one though, the new school one, the mega solar thermal. They're called large-scale solar thermal farms. These seem to be maybe kind of possible, where you've got a whole bunch of mirrors and you heat something up super, 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 super effing hot. I found out that the only limit is the material's ability to survive the heat of the medium. If we had super space-age materials, we could get hotter. We just don't have the materials. But they get the tip of the tower right around 1,000 degrees. I thought it was more, but 1,000 is still pretty hot. And when the tip of the tower is 1,000 degrees, you just, look at me. It's not that far to go. It just goes, and then that's your power plant. So you make the steam right there. Yeah, bro.
So someone just climbed to the top, but they just burned their trip.
Oh yeah, yep. Because our Leah plus 1,000 degrees would be our Leah vapor. Yeah. Okay. But I was just trying to catch up with where we were before. Now you got to get ready to take some notes because I'm going to start dropping all kinds of terminology.
Well, how do they maintain something like that?
Disposable people, high school girls that ask too many questions.
Oh, yeah.
What I would use. Okay, I warned you. Here comes a whole bunch of words, and I'm going to have to move fast because we use a lot of time for math practice. Number 30, hydrogen fuel cells. You must write somewhere in your paper This is not an energy source. This is instead, please look up, energy storage. That is a key distinction. That's why it's like the only writing for hydrogen fuel cells, that it's not an energy source, it is energy storage. Because the fact you have to know that's not written on the whiteboard, it's very difficult to get your hands on hydrogen. Get ready, here comes the paradox. Hydrogen is the most common element in the universe. It's like 90-odd% of everything. Like if you had a checklist and you were everywhere in the universe, almost everything you find is hydrogen. Our planet, because of gravity, is a clump of heavier stuff. So on our planet, hydrogen is like less common than the universe. But still on our planet, whenever you find hydrogen, it's stuck to something. It's everywhere and it's stuck to something. It's clingy, it's desperate, like Jose. So good news, yeah, it's everywhere. Bad news, it takes a lot of energy to peel hydrogen from other stuff. You can do all kinds of chemistry and physics later about how to do that, but right now, we just don't really have a good way to get hydrogen. So you gotta put so much energy into making hydrogen that hydrogen fuel cells are not really very profitable because you spend so much work to get the hydrogen. Everybody please look up, look at me. If this was free, this would be like 100% efficiency. Because from here to electricity, it's like glory. But the amount of energy input to get to this point is less than the energy output of going through the wire. Because the challenge is getting the hydrogen. That's why I said, please look up. Not an energy source, because there's no energy that you're taking. You've already stored a bunch of energy in the hydrogen. So this is just a storage method. The hydrogen itself is your energy storage. You put a lot of work into getting the hydrogen, that's the input, and then you get it out when it goes through the wire, that's the output. Energy storage. Yes? Questions about this? All right, now I explain how it works. This is not that bad. If you don't speak chemistry, I'm sorry, you've got to write this down somewhere. Hydrogen is proton and electron. That's what hydrogen is, no neutrons. One proton, one electron. Notice that weighted pause giving you time to write it down. Hydrogen is one proton and one electron. And if we could split those, we could generate a charge, right? Because you'd have like the positives over here and the negatives over there, you kind of make a battery. Yes? So a hydrogen fuel cell is basically like a segregation machine for positive charges and negative charges. Here comes the entire explanation. Catalyst, metal, semi-permeable electrolyte membrane again. This one's different though, please look up. Plus charges move that way. Gotta know that. And then metal on the other side. Catalyst, metal, positive that way, metal. That's all the parts. Really, you can make hydrogen fuel cells like teeny, 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 teeny. Like you can literally make hydrogen fuel cells like smaller than a fleck of sand. Because there's a little bit of metal, one-way, semi-permeable membrane, a little bit of metal. You can sprinkle a little catalyst on one side, and then as soon as you dump hydrogen on it, everything else is automatic. Because the catalyst splits the hydrogen into electron and proton. Yeah, you always have to ask all the good questions. Really expensive metals like platinum, strontium, rhodium, palladium. Who do you think I am? Well, he doesn't know everything, bro. Here's like my skill set. Like I melt lead and I'm just dragging my train of thought, so I put a little Something about those metals, they're catalysts. They split and cause reactions. Catalysts are things which accelerate chemical reactions. And there's something about the really heavy metals that are halfway in the valence scale. Do you know what valence electrons are? Do you know what a valence scale is? Like between full and empty? There are metals that are right in the middle of the valence scale. So they've got a ring that's half good. And because it's half good, they've got like a lot of room to like juggle. Like, yeah, you can see it with me for a while, but not see it too often. And so they'll split things and then like let them go. I don't know. There's just like catalyzers.
Oh, yeah. Wait, is that on both sides?
No, just on one side. On the hydrogen input side. Because let me do this again without Feinberg's excellent questions. Ready? What? Earlier. B. Damn it.
Oh, okay, okay.
Yeah.
Is this energy storage like? Is hydrogen the only way to like make this kind of energy storage?
There's a lot of different ways to get hydrogen out of things, if that's your question. So there are many ways to store energy into hydrogen, meaning there's a lot of ways that you can spend energies to release hydrogen gas.
No, I'm just asking.
But you're asking, are there other elements that we can split this way? Not very comfortably, because then we're stuck with all of these neutrons. So probably, I'm sure that there's a, like, we can do all kinds of funky chemistry, but I don't think that would really get us into any sort of like realistic hydrogen in particular, because it is the smallest. Look, I can kind of explain that answer a little bit more too. Here's what we're trying to set up. Watch me. Hydrogen splits because of the catalyst, protons on one side, electrons on one side, the protons work their way through because the positive charges only go that way, right? Everybody understand what I mean? Positive charges only go that way? Semi-electrolyte membrane?
Yeah.
Point the way the protons are going. Tight. Okay. Now we've got all the protons on one side equals positive charge, and we're left with all the electrons on the other side equals negative charge. Now we've got that polarity, the ability to do work, we're ready to do electricity. Why hydrogen is, it's a pretty good source of electrons and protons, because that's all you've got, and all you got to do is split them one set at a time. So it's a lot easier to separate one from the other than trying to break up all that into whatever we're doing, what are we going to do with all the neutrons, and like alpha radiation and gamma radiation. Okay. And then the wire goes through, and on the other end, because there's oxygen in our atmosphere, oxygen sort of meets up with the electron and the proton and makes water. And it's just chemistry, don't ask. Proton was there, electrons sort of come around. You know, they're not really traveling, right? There's like a surge of electron concentration pulsing through the wire. Remember we talked about that? Like being the wave, talk about that? What electricity is? Okay. Technically, it's not what I said either, but okay. You got electrons meeting with those protons. They're not going to get back together unless there's oxygen around, but luckily we have a lot of oxygen in our atmosphere. It's like 19%, 21, 29, 20% of our atmosphere. Good? So oxygen plus those parts makes water. Hey, all right, only a byproduct of these is water. So it's pretty convenient. You could run one like on your head, it wouldn't matter. You'd have to have a hose of hydrogen near your head, but yeah. Problem number one, the energy efficiencies of this suck because of making the hydrogen. Problem number two, platinum and the other catalyst metals are very, very, very expensive. Very, very, very expensive. There's like 1 trillion nerds around the world trying to figure out how to make these cheaper, but right now they're very, very expensive. That's why people will crawl underneath your Toyota Tacoma to steal the catalytic converter. Yeah.
Are those metals that they use like naturally occurring, or do you have to like combine them together with other things to make them?
Oh, they're not in the form that you would dig them out of the ground.
Okay.
Platinum, palladium, strontium, and rhodium are relatively rare. When you find them in deposits, they still need some refining. But it is just plain old elemental platinum, rhodium, strontium, and palladium. So kind of like a copper penny. It doesn't look like a copper penny when you put it in the ground, but once you get the copper, you copper, you make a penny out of it. Once you get the platinum, you can make a catalyst layer out of it. Yeah? Now we spin a turbine. Wait, any questions on this? Hydrogen fuel cell? Proton electron? I'm looking at you. So I look like little charge? With the wire? Water comes out? There's oxygen in the parts makes water? This is not balanced. If you speak chemistry, that's not balanced. I don't care. Alright. Number 31 is pretty easy. Please look up. One way to spin a turbine. Look at me. Clog a river. Let out the water and it spins the turbine. Yes? The thing that clogs a river is quote unquote a dam. Your empty canyon becomes a reservoir, not a lake, it's a reservoir. It's a man-made lake. My first act as president, I will rename all the reservoirs reservoirs because I hate it that so many people don't realize that reservoirs are not lakes. Everyone's like, oh, this is such a spectacular lake. Like, no, that's a really nice valley that's been dammed. Sorry, pet peeves. Here nerds. So, dam, clogs the river, builds a reservoir. Now watch me. Look up. Open the dam, water floods through, spin the turbine, make electricity. Okay? Good news, it's renewable because the baby Jesus keeps crying. Bad news, it's not really renewable because our salmon like rivers.
Can we get like fed to the turbine?
Oh, I don't think so. They just can't make it uphill. Salmon are really good at like swimming up and they jump and it's majestic and like they can actually like they'll like surf uphill in waterfalls. Like they can really make like 40-foot waterfalls uphill. Like they land in falling water and kick before it drags them down. This is not a joke. I've seen it with my own eyes. They jump into falling water and then jump into it and jump into it and jump into it. They get to the top and they're totally out of breath. So they got to pull over on the side and go. Every time they like pulled over, they go back. I've seen it. Like it's amazing to watch. But they can't jump like 600 feet. And you watch. They're like trying. It's like sorry, those guys.
Wait, over the dam.
Yeah, but they can't get too high. They can't make that. So they don't make. They don't make babies. They don't. I mean, they just don't go off the river and make babies. You guys know how salmon works? Okay. Another reason they're not renewable is when water slows down, what comes out of the water? Fast moving water can carry, and if it's moving really fast, it can carry big old stuff like your mom, that's right. But as that water slows down, all that stuff settles, right? And so imagine you've got like a rushing river that goes, Arr! So the part that we weren't planning on is that reservoirs are like catchment basins for sediment. So every reservoir in the world is sooner or later going to fill up. And most of our big ones, especially in the United States, because we were really ambitious and we found the biggest rivers, they're going to fill up really, really fast. So renewable, because the baby Jesus keeps crying. Not renewable, because salmon and sediment. Yes? Please ask a question if you have a question. I see that you are writing, so I shall wait a little bit. Because little dams are put in a place with little rivers that don't have the same sediment load on average. Separately, the fish problem might be diminished, but it's not erased entirely. It's easier to solve the fish problem on a little river, because in a little dam, you can build little stack of bathtubs for them to swim uphill. They're called salmon ladders, I'm not sure. There's salmon in Montecito. There used to be a ton. I don't know about salmon ladder. Maybe. What's up, Don?
It's about the salmon.
Okay. I don't want to talk about salmon. Too bad. All right. Number 33, wind power. Do I need to explain how the angry cloud spins a turbine? I know, I'll go back to 32. Thank you, God. What? Angry cloud spins turbine. Okay. I see that you are writing, so I will wait. Please look up. BITD, we used to make these really small so we could put a bunch of them on the landscape. What? Back in the day. Your rap literacy is like really low. Shame on you. What kind of teenager you are. BITD? Back in the day? Alright, fine. So back in the day, we used to make them really small so we could put like a trillion on the landscape and try to pick up all this wind passing through the hills, right? Everybody's writing. Why are you writing? You didn't copy these earlier? You didn't write all the whiteboard crap? Just write like wind blows turbine. Okay. Look, we used to make them really small, like that, across the landscape, trying to all that wind. Does anybody know what pi r squared means? What about circles? Area of a circle, yes?
Yeah.
So here's a funny thing that we recently figured out. If you can make the blade a little bit bigger, or bigger, or bigger, or big as ever, you can make a really big ass circle. And that equals efficiency because remember, you're just translating energy. More wind is more energy transmission, right? It's like more push for more juice. What?
Wouldn't it be more efficient to use like smaller ones though? Because it's like easier for the wind to push?
Nope. We don't want to make it easier for the wind to push. We want to catch more wind so that we can spin bigger magnets past more wires to make more electricity. If we wanted to make it easier for the wind to push, we would just stand there holding a paper or something.
No, but like wouldn't that be really hard to move with like normal wind?
But look at how much wind that's going to catch.
Would you like need more blades though?
So
Oh man.
here comes the math. Aside from your frightening misconceptions about physics, here's the real catch. The real catch is there's like materials limitations. You can't make an infinity-sized blade because after a certain point, they're too heavy for the gears, or they're too fragile for the wind energy, or when you move them, they start to bend and wobble and fall apart. You understand? You can only make things so big. So the lunatic fringe of wind power is making the largest possible blades before they self-destruct. We're dealing with tremendous energies here. That's a lot of wind you're pushing on just a few hinges, or just a few bearings in the middle or whatever. You understand me? So, good news, wind is renewable. The clouds are always angry. Good news, there's a lot of windy places on the planet. This is a pretty darn universal resource, a close to universal resource. Cutting edge, we realize that one big one is better than 30,000 little ones. So if you go to Palm Springs, has anybody driven south on Palm Springs? To Yucaipa or whatever? When you go south on 10 and you drop down that hill into Palm Springs, if you look to the right and to the left, right where you would turn left to go to Joshua Tree, you see like a gazillion. And I want you to notice the next time that you're there, mark my words, please look up. There's like 1 trillion little ones, like 1,000 bigger ones, 100 really big ones, like a dozen really, really big ones, and like 3 big-ass ones. The 3 big-ass ones capture like half the energy. Because of the math of the radius and the circle, you add a few inches and you get like square miles of energy. Yes? Because you just make this a little bit bigger, you're adding a whole lot of area. It's the multiplier, because you're squaring the radius multiplied by 3.1. Yeah.
Might just get rid of all the other things.
Oh, they're already there, so you might as well let them keep making the money. But the funny thing is that most of those little ones don't even run anymore. They're not worth the maintenance fee.
Take it down and use the price to make it.
I don't know how you can scale the parts. My understanding is that there's like a dead field, which is the crappy old ones. And then the future of this generation is the big ones. Actually, the real future is launching these into the jet stream somehow. Because the jet stream has constant 200 to 300 mile winds. It's a lot of energy being like perfectly available energy, like a huge river of energy up there. If only we could make like gigantic kites. And I'm not kidding, there's like billion-dollar engineering projects trying to build like high altitude wind farms that would be anchored to the earth. Now, all of your reasonable skepticisms, I know I'm kind of nervous about it too, but apparently people are trying because they have like unbelievable capacity potential. Okay. Downside, bird blenders.
Oh.
Right. Right. Bird blenders. That was our moment of silence for the birds. Scrivener is making like a post on her book face about how sad she feels. I want everybody to take a moment of silence for the birds. Why on earth would a bird ever need to look up? Think about the evolution of that. Why would birds have the ability to look up? What would that do to them? People up here. Yes? Yeah, maybe. So the animals that are preyed on by falcons, like pigeons, they're pretty twitchy. They dive bomb, and as soon as they land, they look around. But seeing the falcon coming doesn't do you much good because you've got a falcon coming. Here's just a pigeon. You ever seen a pigeon outrun a falcon? No, you haven't. Birds don't look up. Right? So I walked, yeah, that was good, right? You know Robin Williams started as a mime?
Oh yeah.
Is that a fact that you know? He was a street mime. He learned in Paris as like a young man, and then he did that in Central Park. And apparently he was like an exceptional mime. His body language was pretty spectacular. Anyway, I do not compare myself to Robin Williams often. So birds and the thing. I walked underneath a wind farm, and there was like a landscape of bird parks. It was really depressing. But I was shocked to hear that they also kill bats. And I know that bats fly. But I know something that you may not know. Bats are exceedingly agile because of the morphology of their wing. Y'all realize that birds have like two hinges, one in the middle, one in the shoulder? You know that? Because bird wings are evolved from the arm bones. Yes? You may or may not know that the bat wing is evolved from hands at the end of arm bones. So these are shortened to give you the basic gyroscopic motion. But then the shape of the wing is controlled by like hundreds of little bones. They have more, you see how all of yours are stuck together? Your carpal bones are like stuck in three zones? Not in a bat. It's just like, they can just reshape their wing in like a split second. So they're flying and they do these like cool flips, like collapse the wing and turn around and stuff. So I was like, how the hell could they get hit? If you walk underneath these things, they're not that fast. You know, they have gears in them. So when the wind really blows, they just like kick it into fifth gear. But like, they don't really spin that fast. So I thought, how the hell do they kill bats? And I found out that they don't hit the bats. They blow up the bats. Yeah, because you know how a wing works on an airplane? Pressure differential, right? You push the wing through the air. And so by creating force forward, the airplane spreads out air particles over a longer path. So those air particles are more concentrated, so there's relative pressure called lift. You all know how a wing works? Okay, that's how a wing works. You know what I said? Look, longer surface area, right? Because the curve versus a flat, right? Wing. See, that looks like a wing?
Yeah.
Yeah. So you got more surface area compared to this surface area. So when you wedge that into space, you're forcing air particles as they flow over to spread out over a longer area compared to that same number of air particles underneath crowded into a smaller area, right? So more particles per area means that there's like a relative pressure called lift. Okay. Those blades are shaped like that, and they spin like this, and because of the difference in relative pressures, the bat flies right around them, no problem, but when it goes from high pressure to low pressure, the lungs get sucked out of its body.
Oh, no.
Or if the lungs don't get sucked out of the body, at least the blood from their bloodstream floods their lungs and either collapses them or they drown in their own blood.
Oh my god.
Look away though, that'll help. Yeah. Details about bat morphology aside, they really are sort of a challenge. For a while, all the hippies were like, wind power, wind power, wind power, free wind power. And then all the bird hippies were like, boo for wind power, no more wind power. It's really interesting that environmental support for wind power is super divided because they kill views, they add sound, they use a lot of landscape that's visible to people, and of course they blend all the birds and the bats. That's a lot of reasons for hippies not to like hippie energy. Yeah, bro.
Did you think that it's like moved just higher oxygen?
Wherever you put it, you want to put it where there's a lot of wind. And mathematically, wherever you've got a wind, that's what we call a bird highway. You can duct tape a kazoo on it. No, I'm not. Isn't that a joke? The duct tape is not literal, but you make them have a sound either with like a kazoo or a reed. You know how reed instruments work? Like a saxophone? Or clarinet, thank you. Are there any other reed instruments we can cover? An oboe. You can either put a reed on them or a kazoo on them. So as they spin, they make noises. And if you target the pitch, you can freak out birds and scare them off. You can use lights and different sound pitch to scare off birds. They do, but they really lower the efficiency. You're creating turbulence. That's what a reed instrument is. You know, if you've ever played a reed instrument, you can like blow up capillaries in your mouth, pushing air past that reed. So that's a lot of resistance. Does anybody know what I'm talking about? Anybody play the saxophone? And so when you play a reed instrument, you have to force reed. So making them make sound uses up a lot of their efficiency. Anybody want to talk more wind turbines? Fine. That thing about the sound is just a detail. I don't care. Okay. Now get ready to write. There are 4 types of tidal energy, and I'm sorry that you have to know all 4 of them. These poor kids that went to Mexico, they got no idea what they've got coming. They're going to come back and they're like, oh, so much sun, I'm tired from sitting yesterday. They're going to be like, oh yeah, so anyway, their heads are going to explode. I will laugh. They'll have no one to cheat from because they all went to Mexico. Okay. Other classes are just stopping. You know, a bunch of math classes are like, no, no, you know, you're a math student. Have all your other classes totally stopped? I said, nope, I'm a good student. I sit in the front. Things happen. Yep, cool. All right. Number 1 is called a tidal barrage. Please look up. No, look up. Damn it, Emily, hey. There's a bay and there's the ocean, and you build a dam. You You're blocking a bay. So please look up so that you can understand what I'm talking. Look, watch. Then you can draw. Top view. If you turn it this way, you've got a side view. So here's the bay, and there's the ocean. There's bay, ocean from above, and if you turn it sideways, bay, ocean from the side. Yes? Okay. This reservoir is not filled by a river. It's filled by the ocean itself. So most of the time you shut it. And you just let it open so that the ocean water will drain out of the bay or that the ocean water will fill the bay. Like this. When the ocean's at low tide, you release the last high tide, and that spins a turbine, and then you close it so that when your bay is empty, you shut it, wait for the ocean to have extra water available, and at high tide, you open it for a minute, water rushes back in to flood your bay, and in the meantime, it's spinning and spinning and spinning and spinning the turbine. Correct? Well, yes, no, kind of, not really. Here's the, okay. We only built a few of these, and we got rid of most of them because it doesn't really pay off. There's a lot of reasons. Number one, it's, the average tide doesn't do you much good. Do you understand what I mean by that? So, most of the time, these things don't run at very much power. You can schedule, which is nice. You know that in 10,000 years at 4:15 it'll be high tide. So you can schedule your renewable energy, that's nice. But you're only going to get big surges a few times a day. There's like 4 high tides over 25 hours, is that right? I'm sorry, 4 tides over 25 hours? So on average, you've either got 4 per day or maybe just 3 per day opportunities to run this thing. You get a couple hours at high tide, then you gotta wait. And then a couple hours at low tide, and then you gotta wait. And a couple hours at high tide, and then you gotta wait. You know what I mean by that? So it's kind of spotty supply. And there's a separate problem that some of you might understand if you have any experience at all with the ocean. Anything you build in the ocean is going to go to crap in no time. If you've ever done anything with the ocean kills man-made engineering. There's no ocean versus human, ocean always wins. So these are complicated. Plus, does everybody realize that ocean coastlines, especially bays, are super critical ecologically? Remember those coastal wetlands we talked about? What could possibly go wrong with the friggin' blender and the water rushing in and out? So, sensitive habitats, difficult to maintain, irregular supply. Oh, and they only work at the extreme north and the extreme south. Because as you get closer to the equator, there's less and less tidal variation. You all know that? You can find the exact equator in the one place where there's no high tide or low tide. Alright. So tidal barrage, that was just a historical reference for you. This was tidal power 1.0, 1960s, 70s. It didn't work out, we got over it. Southern Argentina, I think Iceland, northern British Columbia, and one other that I think might be Ireland. And they built them, and it's well, that was a waste of time. And the one in Argentina, the ocean killed it, and people were yeah, whatever. And they just abandoned it. You can drive up to it. It's hard to find the right place. You need really steep cliffs to an entry to a small bay, crash. Okay. Number 2, these are apparently a lot more feasible today. Please look up. It's the same. Wait. It's the same concept, 2 different ways. A submerged turbine is a turbine standing up to catch a current, and a turbine reef or a tidal reef is in the intertidal, right against the coast. Surge forces, wave action. You know what I mean? You ever been on a steep section of sand and the water rushes up, splashes your feet, and climbs up your shorts and then goes away? Okay, that surge can spin them laterally or a strong current can spin them in the opposite orientation. Ask me a question now if you're going to ask something. Take a second to draw, you're going to take a second to draw. Yeah?
Ever just do that with like actual waves?
Waves are hard to target because wave action depends on 3 variables that move them. The size of the swell pulls it further out to sea or close. You know the rolling ball. You ever seen like surf models with like the rolling ball? Like, okay, so they move up and down away from the coast. Plus tides move them up and down from the coast. Plus tides move them up and down in your vertical axis. So catching waves is really difficult. But if you're at the average tide line, there's always water splashing up or down on a steep section. So you're catching the surge force, not the wave force.
Or it has to be on a slope.
It has to be on a slope for tidal forces. After you finish drawing, I'm going to say things. So you can have a minute, but not much more. Oh, dang it, you can't even have a minute. Look. First of all, sensitive habitats. Second of all, engineering in the ocean, good luck. Third of all, we can't quite make these things profitable, but there's a hint, look at me, that these ones, the submerged turbines, they're about to go big scale in Europe. An American company just got like a gazillion-dollar contract to install like a gigantic field of these, the current-based ones, because they crack the engineering of the gearbox. They don't spin very fast. And then there's gears that crank up the turbine. You know what I mean by that? Gears? There's like cars, you know how motor moves at like wheel speed. So the current just barely spins it, and then there's like a gearbox that accelerates the turbine. Yeah? So you just use a screen to block out the whales, and all the other stuff can just swim through. It's not fast enough to blender them. This is just too sketchy. As far as we can tell, there's like too much moving sand and like the ecosystems are too sensitive. This one doesn't seem to be happening as far as I can tell. There was like popular mechanics 10 years ago and I haven't really seen it anywhere. But this seems to be like people are getting ready for it. If you have a question, ask now because I'm about to make you write something different. Okay, everybody write this down. Low boiling point. For number 3, ocean thermal, please write down low boiling point. Science nerds, what is the boiling point of fresh water? 100 degrees Celsius, that's why it's 100 degrees Celsius, which is equal to what in Fahrenheit? 212. Can the ocean get to 212 degrees? I mean, is there any place where you find surface water at 212 degrees? No, there isn't. So we can't boil water. But if you've ever sprayed Windex on the windshield, you notice that it evaporates pretty quickly. Anybody notice like on a hot day you spray it and you can't even get a chance to wipe it before it's gone? You know what I'm talking about? You've had this experience in your actual lives? That's because ammonia has a low boiling point. It's one example of things that evaporate at lower temperatures. They go from liquid phase to vapor phase at, room temperature, high 70s, low 80s. Can the ocean reach high 70s, low 80s? It sure can. If you go to the northern Sea of Cortez in August, it'll be like high 80s, low 90s, like piss water. Unpleasant. I've been peed on by my children, of course, and others. And when in the Sea of Cortez, I just kept thinking that someone had peed on me and it was grizzly and I had to get out. It was just not pretty at all. I want to go with Sophie Tate to her house in the Sea of Cortez, but I'm afraid that the water will feel like urine. I don't like that feeling. Okay, watch. Urine temperature water. Urine temperature water. And watch me, watch me. You've got a pipe that puts a liquid into that water, and that fluid has a low boiling point, so it comes out of the pipe as vapor form. Right? You understand what I'm saying? And that can spin a turbine if you got the right pressure mix stuff. So by using hot surface water to create vapor of a fluid with low boiling point, your heat source is the ocean surface to spin a turbine with vapor. Questions about that one? The challenge is finding the liquid. Just so you know, the challenge is finding the liquid. It's difficult to find something you can do that with. It was a nice idea. We haven't built these because it was just too much of a good idea. Please ask me something. Yes?
Wouldn't the steam be steam of like whatever's in the...
That's right. So it's just evaporated, low boiling point fluid, like ammonia vapor, not water steam. I shouldn't have written steam. I should have written vapor.
And that's what spins.
Yes, that's right. When I wrote steam, everybody thinks I'm talking water.
Yeah.
That's my bad.
And then it like
Yeah, so it's not steam. I'm gonna get rid of that right now. What comes out is vapor. Low boiling point fluid. Like alcohol fumes, you know? You pump alcohol and the alcohol gets hot and it comes out as alcohol fumes. Yeah? You all realize that when most things go from liquid to vapor, they expand? So if your pipe is the same size the whole way, it comes out under pressure because it's trying to expand into vapor form, right? So that expansion, that's the force that spins your turbine. Yes? Questions? I have to move on, I'm sorry. I spent too much time on that today. Oh crap, we're gonna run out of time. I will paint you a pretty picture. Jose is playing in the bath. There's water on my head. All my analogies are bath analogies because I'm in charge of bath time on Wednesday night. Okay. It's not that hot. It's kind of a crap show. I can hit fights and like splash water everywhere. Yeah, it's not the least cute thing in my life. All right. And I'm not actually in the bath. Let's keep it PG. I'm in a pool wearing like a bathrobe. Okay. And many layers of clothing. 5. Chainmail. Okay. The part I want you to focus on is this. Not my bath experience, but this. Okay? Everybody has water experience. So I'm going to give you a little visual demonstration, and then we're going to get to the nitty-gritty. If this is the surface of the water, and I have a tub, this is an airtight cup. I can like splash water on my head, okay? No water in it. Okay? And I push that down into the water. What have I trapped inside my cup? When I let it go, what will happen? Right? Because it's like trapped a bunch of air and the air wants to rise because that water wants to level itself, correct? Because we're sharing the pressure with the fluid. Okay. Next, I take my cup, shake out the water. There's no water in it, but it's water. And then, what's in my cup now? That's right. If I go like this, I got water like fill my cup. So I go like this, okay, got the water in it, yeah? What if I go and then I pull it out? I'm suctioning water up, right? And so if I let it go right here, what will it do? Because the water wants to stay at level, right? Everybody experience that? Water suction wants to fight itself. And what if I pull it all the way and go? What happens there? Swoosh. Okay. Now, I leave the bathtub, I go turn on the stove, I get my nail on fire, I heat up a nail, and I go tss, and I melt a hole. Yeah? I go back to the bath and I put my chainmail back on. And I got my thing with a little hole in it. And now when I push this into the water, what's happening at that vent hole? The what?
Air.
Like 4 of you are kind of mumbling something.
It's
What?
getting pushed out.
What is?
Air.
Right? And what if I get right near air level and I start to pull it up? What happens at that air vent?
It gets pulled in.
Right? So it's going, right? Air pushing out and sucking into the little hole because the water wants to level itself. Yes? But I had to do all the work on this. What if I just attach this to the side of the bath and then I make the water move? What's happening at the vent? Right? Because I'm like making a piston of water move up and down inside that thing. That's called an oscillating water column. Like that. You use, please look up, you can write later, sea surface action to move a water piston inside an air pocket with a vent to translate the air movement to turbine spinning. Yeah? Imagine, you can build these on a pier so they're bankable. You can just launch them out into the ocean. You can go 100 miles out to sea and there's still water moving across the surface, right? There's always water moving across the surface of the ocean. Some parts of the ocean in particular, there's like a lot of ocean surface. So you can make like floating islands of these little cups that are all just picking up wave action, surface action. You can put them on piers. You can put them on oil rigs, barges. So first of all, please look up, they are bankable. Second of all, in many parts of the ocean, they are nearly constant. Because there are some places where the ocean's always moving. You know, the Pacific is very peaceful. Pacific. But other parts of the world, you know, they got a lot of ocean action. And finally, there is some suggestion that this might add intertidal habitat. I don't like to play with my coastlines, because I surf and I free dive and I fish and I just like the water and stuff. I'm a nerd. But some people suggest, hey, maybe we could farm oysters on it, or maybe we could put fish pens underneath it, or maybe we could double duty. We're already kind of messing with the ocean in some places. I don't know. Kind of nervous about the ecological implications, but kind of a lot of potential to make energy. I wish we could have talked about something else, but I ran out of time today. God, I'm a worst teacher. But thank you, Amin.